rigid body kinematics. Okay, so today, does that make sense as far as what that exam will cover? Okay, so today what we're going to do is just briefly cover oblique central impact. Then following that, I'm just going to make a few comments on material we'll not be covering, which is the tail end of Chapter 3, some special topics there, other special topics besides the impact issue. And then we actually are going to skip Chapter 4, which is where you have systems of particles interacting. And then we'll actually go ahead and then get started on Chapter 5, which will be an introduction to rigid body kinematics. And in what we'll get to today is rotation. And we might get to, related to that, we might have time to get to absolute motion, it's called. This is a type of analysis, type of geometric analysis related to rigid bodies. Very important. So this stuff we're here in the Chapter 5 material, the rigid body material, this is a really important area in that to get going on. Okay, so let's start with oblique central impact. And I think what I'll do is show you briefly a description of the problem setup in the text. And what you'll notice is here's mass 1 coming in from the left, and then mass 2 coming in from below. And this is with their associated incoming velocities. So each of those masses are carrying some momentum, linear momentum with them. Doing oblique central impact, we're assuming the particles are spherical in their shape, and that there's no friction imparting kind of like spin or English onto the particle, like on a billiard ball, that kind of a thing, where that that kind of spin motion actually on a billiard table, the spin motion, the contact of the ball with the fabric of the table actually creates some geometric effects in the motion of the ball. So we ignore those here just to keep the analysis simpler. And then also what we have to do is we have to have a well-defined tangent line to the contact, a well-defined tangent line to the contact. So once we have that defined, then that would establish a normal, a unit normal direction, and then the two masses will interact with one another, and they will interact as shown right here, where they have equal and opposing impulses in the normal direction, equal and opposing impulses in the normal direction. And here's what an impulse is it's typically in an impact condition, it's over a very short duration of time. Very short duration, in the order of milliseconds, several milliseconds. Automobile accidents, typically what happens is when you have injury vehicle accidents, the motion is actually occurring over just a few milliseconds, maybe 6 or 7 milliseconds typically. And what happens is our body can handle accelerations up to certain levels, and then we start to do damage to our body tissue if you exceed those acceleration levels. So automobile impacts, typically the deceleration's occurring over about 6 or 7 milliseconds typically. Okay, so there's a very short duration of time. Sometimes these forces can actually spike up to tremendous values. In summary, as far as how do you do these problems now, what you notice is if you know the incoming angles, and you know the incoming velocities and masses, so the incoming information is known, then how do these masses then depart from that impact, after the impact? And so the way that we do the analysis is, think about it this way, if you ever forget, which you probably will over the course of the summer. Okay. If you look along the tangent line here, there are no forces in the tangent direction. No forces between the interaction of the bodies in the tangential direction here. So that means then each particle, each mass separately, must have conservation of linear momentum in the tangential direction. So we can write, and I wrote a little summary over here on the side. I don't know if it shows up on the screen or not, but in the tangential direction, each mass, and I'll say it out loud in case this doesn't show up on the DVD. In the tangential direction, each mass must carry conservation of linear momentum in the tangential direction. So we have two equations then with these four unknowns. There are four unknowns over here, the two outgoing velocities and the angles at which they're departing from the tangent line. So we get these two equations. Then in the normal direction, since these impulses are equal and opposing, we have conservation of the system's momentum, linear momentum in the normal direction. So that's another equation. So delta G in the normal direction equals 0. So that's three equations with four unknowns. And then finally, we have the types of materials that are interacting, and then we can write another equation related to the coefficient of restitution, which, remember, is the relative velocity of separation divided by the relative velocity of approach. And depending on the two materials interacting, the coefficient of restitution, small e, then could be of values ranging from somewhere close to 0 up to numbers close to 1. What you typically do then in summary is you solve, once you have your four equations and four unknowns, they're linear equations, you solve for the outgoing velocity values. And once you have those, then you work on solving for the angles at which they're departing from the tangent line, theta 1 and theta 2 prime. Okay, so that's just a real quick summary of the approach. It's just you end up with four equations and four unknowns unless the problem is simpler, where some of it maybe one of those unknowns reduces out. So what I thought we'd do is tackle a problem. Why don't we look at number 272? I'll put it up here on the screen. We did a problem last session, which is where we had a brass plate and a steel plate. And now this time, though, we want to do a oblique central impact problem. So we have two identical steel balls this time, and we know the incoming velocities and the angles at which they're making, and we also know they've defined this as the x-axis, which would be our tangency axis, and they defined a y-axis, which would be our normal axis or transverse to the tangency. And we know the incoming velocities and the angles at which they are coming in at. What we want to know then is what the velocity is immediately after impact, and then the percent loss in kinetic energy in the system. They don't even give us the masses, but they just mention that they're identical. So that's going to imply that the masses are going to drop out of the solution process. Any questions on that? Okay. So this mass is coming in and it's carrying some momentum, and so it has mv1, and I believe it was 4. Was it feet per second? Yeah. Okay. So this is going to be 4m is its momentum it's carrying as it's moving downward. And that's going to be in our normal that's opposing to our normal defined direction. They call that the y-axis. I'm just going to call that our normal. The other mass identical is coming in, and remember these are actually points treated as particles, and they're coming in at what angle? From
the vertical right there.
From the normal?
Yeah, going that way.
Okay, so it's actually 60 degrees off of this tangent axis. This is called their x-axis. And so 60 degrees is the incoming angle. And so this thing's coming in, and you said at what speed?
6 feet per second.
Thank you. So we have m times v2 is going to be 6m then, is the momentum being carried by that lower particle. The incoming angle of this one, here's the angle incoming, and here's the angle from the tangency of this one, happens to be 90 degrees. So this is our theta 1, and this is our theta 2 down here. Now, they're going to then depart at some other momentum, and so it's going to be carrying mv1 prime at some angle theta 1 prime, and this one's going to end up departing at some other angle at some mv2 prime momentum and some unknown theta 2 prime angle. So, in the tangency direction, we have conservation of momentum for each mass. So M1, we have delta G in the tangential direction must equal 0, conservation of momentum for mass 1. Now look what happens here with M1, the first mass. It's coming in at 90 degrees to the tangency, and it leaves at some value here. So let's go ahead and write that change in energy, linear momentum. And so that's going to be m v1 prime in the tangent direction, right? Cosine theta 1 prime must be equal to the momentum in the tangential direction coming in, and that was mv1 cosine of 90 degrees. And we can see that this goes to 0, which means that cosine theta 1 prime must equal 0, which implies that theta 1 prime must also equal then 90 degrees. This one comes in perpendicular to the tangency, has to bounce off and go right back up. So that was a simplifying situation in this particular problem. Instead of getting 4 equations with 4 unknowns. So we're already able to figure out one of those unknowns. Any questions on that? Let's do the same thing now for M2. M2 in the tangential direction, its momentum must be conserved. So here's M2 down here, and it's coming in and it's carrying momentum initially to the right, which is going to be 6m. I'll go ahead and use those values. Should I write it in general, or should I put the numbers in like I just did there with the 6? Do the general first? Okay. I think I was pretty good about that up there, yeah. So incoming, and again in the tangential, we have the, actually I have the outgoing, let me be consistent there. So the outgoing is going to be mv2 prime cosine theta 2 prime, that momentum in that direction of this lower mass must equal the momentum before the impact in that same direction, which is going to be mv2 cosine 60 degrees.
You don't have to account for like being under, like the angle being below the T?
No. It's what we're interested in is the momentum being carried by this mass in that direction, in the direction of the tangency, and the other mass. So there's conservation of momentum, and the reason is there's no impulse. There's no impulse in the system in that direction for either mass.
So
For
you're
I.
not looking at the system.
No, we're looking at each
Looking at
mass.
Each individual mass.
Each mass. That's why I labeled this M1. M1's conservation of linear momentum in the tangent direction, and similarly here for M2. Okay. So then you can see the mass divides out here, and the incoming velocity on number 2 was 6 right there. And so we have two unknowns sitting right here. We have V2 and theta 2 prime in there, and that's equal to 6 cosine of 60 degrees is a half. So that's going to be equal to 3 over here.
V2 prime cosine theta
Cosine what?
prime? V2 prime cosine theta 2 prime?
Right.
You're missing a
What am I missing?
prime. A prime.
Oh, right here. Thank you. V2 prime. Okay. So we have two unknowns sitting right there. So let's go and grab our third equation. Third equation is going to be in the system. Conservation of momentum in this normal direction for the system. So we're going to have delta G, let me come over here. Delta G in the normal direction must equal 0 for the system. So everything, remember these are vector quantities. So what we're going to have is the incoming, the before impact momentum must equal the momentum after in the normal direction. So we're going to have negative mv1 straight down, and this guy upward momentum is positive mv2's momentum, and we want sine of 60 degrees there. That's the momentum in that direction before the impact. Then the momentum using the defined quantities over here after the impact is going to be the upward component of that, which is mv1 prime sine of theta 1 prime minus mv2 prime sine theta 2 prime. But things get a little simpler because of a piece of information we learned earlier, is that theta 1 prime over there was 90 degrees. So theta 1 prime is 90 degrees, so this term goes to 1. And the masses divide out in every term because they're identical. And we know our incoming velocities of 4 and 6 right here. So we have minus 4 plus sine of 60 square root of 3 over 2 times 6. That's 3 square root of 3. And that must be equal to V1 prime minus V2 prime sine theta 2 prime. Okay. How many unknowns are floating around in these equations? We have an equation down here involving 3 unknowns. And then we have an equation here involving 2 of those 3. Yeah. So we have 2 equations with 3 unknowns here. In the general situation, showing the incoming angles, different 2 velocities, and outgoing 4 items, you typically have 4 equations. Okay. So anyway, we have 2 equations with 2 unknowns. There's 2 equations, 3 unknowns. Okay, got to say that right. So we need another equation that relates to the materials that are interacting with one another. It happens to be steel on steel, which I believe they said was 0.6 for the coefficient of restitution. So doing the coefficient of restitution being equal to 0.6, that's the relative velocity of separation. And we just take the absolutes of those, divided by the relative velocity of approach. So the relative velocity of approach in the denominator here is going to be the sum of these 2 velocity components. So it's going to be V1's value, which is 4, plus the sine component of V2's value of 6. So it's going to be V1's value of 4. I'll just write it down. And that would be on the sine of 90 degrees right there, if you want it. Okay. Plus V2's value, sine of 60 degrees. We'll substitute those numbers in there in a second. And so that denominator will clean up. This becomes a 4. This value becomes a 6. Sine of 60 was square root of 3 over 2. So this again is 3 square root of 3. So we have 4 plus 3 square root of 3. The relative velocity of approach. The relative velocity of separation is going to be, using the piece of information from earlier, that theta 1 prime was 90 degrees. This mass is bouncing straight back up, perpendicular to the tangent line, and it's carrying a velocity of v1 prime. v2 prime has a sine component downward. Those 2 are then additive. So it would be a v1 sine of 90 sine of theta 1 prime v1 prime sine theta 1 prime minus a minus v2 prime sine theta 2 prime. Those become, since v1 prime was 90 degrees, that becomes just v1 prime. Minus the minus becomes plus v2 prime sine theta 2 prime. If necessary, we could have slapped absolute values on those. Did I write it down right, or did I make a mistake somewhere?
Why is the denominator addition?
Think about it. What's the relative velocity of approach? One mass is coming downward, right?
Be negative then?
Okay?
Well, think of it like this.
Well,
It's the angles that are compensating for the sine effect.
exactly. So if I wanted to stick with the numerator, I followed carefully followed carefully the sense of positive on our normal, didn't I? On the numerator. In the denominator, if I did the same thing, I would assign a -4 to this, and then this would be minus a minus, I'm sorry, no, it would be minus a positive value.
Right.
Minus a positive value, and that would give the net sum of negative values that we'd then take the absolute value of. I don't know if you followed that. The best way to do them is look at it and just make sure that what you end up with is consistent. There should be a net sum showing that approach. Is that right? Okay. So we end up with this. Then now we have, this is our third equation we needed to handle those three unknowns. And then the summary I gave you a few minutes ago is that, okay, you write these equations, you get your 4 equations and 4 unknowns, then you solve for the, what? Angles or the velocities?
Velocities.
Find the velocities first, because the angles are tied up inside the trig functions. So it'd be better for you to figure out the velocities and then worry about the trig. So let's do it. We have theta 2 prime in there. Oh, here we go. Sine theta 2 prime is in this equation and our third equation over on the other board. So if we solve this one for sine theta 2 prime, then we could substitute the expression involving v1 prime and v2 prime into that other equation over there. So if I label these, when I solve systems of equations, I don't know if you folks do this in your work, because it can get confusing to look at your work later and go, oh,